Hello students, this is the second video on long transmission line modeling. So let us quickly review what we have studied in the last lecture. What we have done is, we derived a common voltage and current equation at any point on the transmission line, and that came out to be Vx is equal to Vr plus IRZC by 2 into e power gamma x plus Vr minus IRZC by 2 into e power minus gamma x. Similarly, Ix is equal to A1 e power gamma x minus A2 e power minus gamma x by Zc. We found out the constants A1 and A2 by using initial conditions. Next, if you observe, I said that, let me remove this Ix equation. This V1 is the wave which is traveling from sending end to receiving end, and this V2 is the wave which is traveling from receiving end to sending end. That means this is the reflected wave. So if this is our receiving end, there is a wave traveling from sending end to receiving end, and when it reaches the receiving end, a part of the wave will reflect back and a part of the wave will travel to the load. This is called as incident wave, this is called as reflected wave, and this is diffracted wave, right? So whenever there is a receiving end, the wave partially reflects. This is that wave. If I model the receiving end, it will be like this, right? This is the receiving end impedance, and this is receiving end current, and this will be VR. So what will happen if I make ZL is equal to ZC? Let us see. ZC is our characteristic impedance. So what if ZL is equal to ZC? That means what will happen if load impedance is equal to characteristic impedance of transmission line. So in this case, if this is ZC, what will be VR? IR into ZC, right? If VR is equal to IR into ZC, what will be our second term? These two will cancel each other, and the term V2 is becoming 0. So what does V2 indicate? It indicates the reflected wave. So I can tell that there is no reflection here. There is no reflection. In other words, the traveling wave will see no receiving end. It thinks that there is no end to the transmission line, there is no receiving end, or I can tell that the line length is infinite. There is no receiving end because there is no reflection. So if ZL equal to ZC, the transmission line is also called as infinite line. It doesn't really mean that the line length is infinite. It means that the load impedance is equal to characteristic impedance. This kind of line is called as infinite line. So in the question, if he mentions the line is infinite, then you should take your load impedance is equal to characteristic impedance. And don't confuse, sometimes this characteristic impedance is also called as surge impedance. I will explain this afterwards. For now, just remember. Next, After this, if we expand our Vx and Ix terms, and if we substitute x equal to L, and if we substitute x equal to L, this will become Vs and this will become Is, because x is the distance from receiving end. So after substituting this, our real ABCD parameters came out to be cos h comma L, Zc sin h comma L, sin h comma L by Zc, and cos h comma L, right? Now, if I want to do the load flow analysis, I need to represent the transmission line by some model like T circuit or pi circuit. And in the first lecture, I explained that generally we will use pi model. Why? Because it will not add an extra node. So we will try to represent our ABCD parameters in pi model. Let us see how can we do that. So this is our pi circuit. This will be Z dash, and Y dash by 2, Y dash by 2, and Z dash and Y dash are not the original impedance and admittance of the transmission line. These are just the representation of the ABCD parameters of long transmission line. These are not the original values. Okay. So for this pi circuit, ABCD parameters will be 1 plus Y dash Z dash by 2, Z dash, Y dash into 1 plus Y dash Z dash by 4, 1 plus Y dash Z dash by 2, right? We derived this in the medium transmission line analysis. So from this, I can equate Z dash and Zc sin h comma L. So by equating B, what we will get? Z dash is equivalent to Zc sin h comma L. Now, Zc is root over Z by Y into sin h comma L. Now, if I multiply numerator and denominator by root Z, what will I get? Z by root over yz sin h comma L, right? And this is gamma. So, Z by gamma sin h comma L. Now I am multiplying the numerator and denominator by L. So this is equivalent to total impedance of the transmission line into sin h gamma L by gamma L. Is this okay? I am erasing this. So Z dash will be equal to Zc sin h gamma L, which is also equal to Z sin h gamma L by gamma L. Here Z is the real impedance of the transmission line. Next, let us find out what is Y dash. Now I am equating the A parameter, that is 1 plus Y dash Z dash by 2 is equal to cos h comma L. From this I can write Y dash by 2 is equal to cos h comma L minus 1 by Z dash, right? And I am substituting the value of Z dash, that is Zc sin h comma L. And if you do some trigonometric manipulations for this, the value turns out to be tan h comma L by 2 by Zc, right? Now I am expanding this Zc. This will be root over Y by Z tan h comma L by 2. I am multiplying the numerator and denominator by root y. So this will be y by, this will become gamma, tan h gamma L by 2, right? Now I am multiplying the numerator and denominator by length L. So this turns out to be y by gamma L tan h gamma L by 2. Now I am dividing both numerator and denominator by 2. So our final equation is y by 2 tan h gamma L by 2 by gamma L by 2. Is this okay? Now I am erasing all this. This implies y dash by 2 is equal to y by 2 into tan h gamma L by 2 by gamma L by 2. So these are the z dash and y dash by 2 values that we obtained from this pi model. Now let us see what will happen if we analyze the same thing for medium and short transmission line. That is, if we decrease our length, whether this analysis is valid or not. So if we decrease our length, sin h comma L will become gamma L and tan h comma L by 2 will become gamma L by 2, right? So from this, what will be our z dash? Z into sin h comma L will become gamma L. Gamma L by gamma L. So z dash is actually equal to z if we are decreasing the line length. And let us see what will happen to y dash. Y dash by 2 is equal to y by 2 into, this will be equal to gamma L by 2. Gamma L by 2 by gamma L by 2. So this is 5 by 2. If you observe here, if I decrease the length, our z dash and y dash are actually equal to the real impedance and admittance of the transmission line. Otherwise, I can tell that the approximations which I made while analyzing short and medium transmission line, they are actually accurate. So this is proved here. Take the ABCD parameters of long transmission line and decrease the length, and that turns out to be ABCD parameters of the medium transmission line. That's it. Next, let us see a problem based on ABCD parameters. Here it is given that a 500 km long line for which the per kilometer line impedance and admittance values are z and y. So these are per kilometer. Calculate the ABCD parameters. We know that ABCD parameters are cos h comma L, ZC sin h comma L, sin h comma L by ZC and cos h comma L, right? So to calculate these parameters, we need to know gamma and ZC. So first let's calculate them. Gamma is nothing but our propagation constant. And can be calculated by root over z into y. These are per unit length impedance and admittance values. Next, let us see how to calculate ZC. ZC can be calculated by root over z by y. So this comes out to be root over 0.1 plus say 0.5145 by z 3.1734 into 10 power minus 6, and this is equivalent to 406.4024 at an angle minus 5.5 degree ohm. I took this problem from NPTEL. You can check there. Next, if you want to calculate the propagation constant, this will be equal to root over 0.1 plus j 0.5145 into j 3.1734 into 10 power minus 6. If you observe here, this is square root over complex terms. This is square root over complex terms. And next, we need to substitute these complex terms in the hyperbolic functions. So you are getting right how complex this calculation is. So to simplify the analysis, what we will do is, we will approximate our ABCD parameters by using Taylor series. Here, the Taylor series of cos h comma l will be equal to 1 plus gamma l square by 2 factorial plus gamma l power 4 by 4 factorial and so on. Since it is just an approximation, we will be considering only first two terms. This q rise to 1 plus gamma square l square by 2, which is equal to 1 plus zy into l square by 2. This I can write as 1 plus z into l and yl by 2. This q rise to 1 plus zy by 2. This is the value of cos h comma l, right? One plus yz by 2. Similarly, let us calculate sin h comma l, which is equal to gamma l plus gamma l cube by 3 factorial and so on. We will consider only first two terms. If I take gamma l common here, this will be equal to gamma l square by 3 factorial, which is gamma l into 1 plus, we have already seen this will be yz by 6. And what will be gamma l? Gamma l is root over zy into l. See, always remember, we should calculate gamma by using per unit length values. That is root over z into y. This is per unit length impedance and this is per unit length admittance. Or remove the term unit. You can tell impedance per kilometer and admittance per kilometer. So here, if I bring this term L inside, this will become root over ZL into YL. Now this is our total impedance and admittance. Here it is impedance per kilometer and admittance per kilometer. Okay? Next. So I can write this as root over YZ into 1 plus YZ by 6, which is root over YZ into 1 plus YZ by 6. Now let us calculate B. B is equal to ZC sin h comma l, which is root over Z by Y. Sin h comma l is root over YZ into 1 plus YZ by 6. This will be Z into 1 plus YZ by 6, right? Next, let us calculate C. C is equal to sin h comma l by ZC, which is root over Y by Z into root over YZ into 1 plus YZ by 6, which is equal to Y into 1 plus YZ by 6, right? So B is z into 1 plus 5z by 6 and C is y into 1 plus 5z by 6. Let me write it here. B is z into 1 plus 5z by 6 and C is y into 1 plus 5z by 6, right? And A is equal to D is equal to 1 plus 5z by 2. Now these are the approximated ABCD parameters. 1 plus 5z by 2, z into 1 plus 5z by 6, y into 1 plus 5z by 6 and 1 plus 5z by 2. If you observe here, there are no hyperbolic functions. That means your complexity got reduced. Now if you go back to the previous problem, you can solve this, you can find this ABCD parameter simply by just substituting y and z, and it is a normal calculation, right? So you can do that easily. So this is the advantage by using the Taylor series. And students, this is for now. In the next lecture, we will see per unit ABCD parameters and we will proceed to lossless transmission line, which is very interesting. And after that, we will see wave traveling analysis. Right? Take care. Bye.